Bismillahirrahmanirrahim. Getting started with Verilog, I choose this circuit as an example. This is a half-adder circuit. This gate level implementation of a half-adder. Inputs and outputs are shown. This is the block diagram of a half-adder. In block diagram, we don't know what is inside the block. In Verilog, this is known as a module. A module can be any circuit. A module, by writing a module, we start with keyword module and end this module with keyword end module. This is half adder, so we name our module half adder. It is a declaration of a module. After name declaration, we assign inputs and outputs like this. Outputs comes first, then input. After declaration, we need to define inputs and outputs explicitly as well. There are several statements and all of them ends with semicolon. Now, to code an XOR gate, we write XOR, and for AND gate, we write AND XOR sum, that is output, and AB, these are the inputs. Similarly, for AND gate, carry is the output and A, B are the inputs. We have designed our half-adder module. Now writing test bench code. We have designed our half-adder module. This is known as UUT or DUT, design under test. We need to test our module. With the help of test bench module, we can simulate the circuit and show up and get output waveform. Test bench code is connected to half-adder block like this. There are some rules to follow. Test bench is connected to UUT and we need to define these outputs as data type. And while UUT, in UUT, input variables are declared as wire data type. In test bench, input variables are declared as wire data type. And in UUT as well, input variables are declared wire data type, while output variables are declared as red data type. These outputs are connected to the input of UUT. Let's start writing test bench code. It starts with module and ends with end module like before. Declare inputs and outputs. Reg is the input to half-adder. Half-adder instantiate, and we write inputs and outputs in the brackets. This is initial block and we write rest of the test bench code in this block. It starts with begin and ends with end keyword. There are 4 possible combinations of input. We will check each value one by one. A is equal to 1, B 0, it means A is 1 bit long, B is for binary, and 0 is the value of A. Adding 10 nanosecond delay. Here A is equal to 0 and B is equal to 1. Similarly, add all other cases. in initial there is another initial block, and add these two lines in your test bench code. It will help in displaying the waveform. Now these are the waveform. A is equal to 0 for 10 nanosecond, A is equal to 1 for 10 nanosecond, again A is equal to 0 for 10 nanosecond, and A is equal to 1 for 10 nanosecond. So let's start with EDA Playground. It is an online simulator. You can get it right in your browser. No need to download. There are 3 windows here, and on the left there is a panel. This is save option. This window is for your code. This is the log, and this is the test pen window. Now this is Verilog here. Here tools and simulators. Check this one and select open EPWave. I have already written my code. This is my code here. I just recheck it and I find just add to 10 nanosecond delay and finish then. Now let's run our code. You can check this code on my blog as well. This is our waveform. These are our waveforms. At 0 nanosecond, A, B, and carry and sum all are 0. At 10 nanosecond, B goes high, sum goes high, carry is still low. 10 nanosecond difference. At 20 nanosecond, A goes high, sum goes high, while carry is still low. At 30 nanosecond, A, B, and carry goes high while sum goes low this time. I hope you understand. Thanks for watching. Goodbye for now.